All right, close your eyes for just a second. I want you to imagine you're holding a freshly poured, warm cup of coffee on a really crisp morning. Picture the frost on the window pane, the faint trails of steam rising from your mug, and that sharp contrast of the chilled morning air against the piping hot ceramic resting right there in your palms. Do you feel that warmth spreading straight through the mug and into your skin? Well, what you're actually feeling in that intimate, everyday micro moment isn't a physical substance at all. It is literally energy in motion. Scientists call it heat. And today, we're going to decode exactly what that means.
Welcome to this explainer. Today we're going on an absolutely incredible journey to understand the invisible mechanics of heat and thermodynamics. We're going to scale all the way from the relatable comforts of our everyday lives right up to the fundamental rules governing the very edges of the universe. It's really a journey into the hidden engine running the background of our entire reality.
So, let's start by getting our terms straight. What exactly is heat? Well, it's a form of energy, but specifically, it's energy in motion. And it follows a strict, unbreakable universal rule. It always transfers from a hotter body to a colder one, never the other way around. Every single time you boil water on the stove, burn fuel in your car's engine, or even just run a fever, heat is flowing in that one specific direction, constantly seeking balance. Now, scientists actually measure this flow of energy using a metric called joules, which is the standard unit of energy in physics. To put that into perspective for a second, exactly 4.2 joules is the energy equivalent of 1 calorie. So when we talk about burning calories on a treadmill or reading the nutrition label on your favorite snack, we are literally talking about this exact mathematical transfer of thermal energy. Crazy, right? Here's our roadmap for today's explainer. We've tackled the mystery of warmth, and next, we'll look at how heat travels, the grand laws of the universe, water and state changes, Newton's law of cooling, and finally, the universal heat engine. Section 2. How heat travels, the 3 epic transfer mechanisms. Okay, so how does this energy actually get from point A to point B? There are basically 3 distinct ways this energy moves through our world. First up, we have conduction. This requires direct physical contact. Think about a cast iron pan sitting on a stove. The vibrating, heated atoms at the bottom bump into their neighbors, passing the energy up until you accidentally touch the handle, and the heat travels straight into your hand. Second is convection. Now, this involves fluids and gases in motion. Warm air expands, it becomes lighter, and rises, while cool air falls. It's exactly why campfire smoke billows up into the night sky, and why the second floor of your house always feels way stuffier and warmer than the first floor in the middle of summer. And the third way? Radiation. But what's truly mind-boggling about that third mechanism, radiation, is the sheer scale of it. Unlike conduction or convection, radiation doesn't need any physical matter whatsoever to travel. I mean, think about it. The sun successfully heats the Earth by sending pure electromagnetic energy across 93 million miles of completely empty, freezing space. It's an absolutely massive transaction of energy happening continuously, every single day, just keeping our planet alive. Section 3, Laws of the Universe, the Grand Rules of Thermodynamics. Let's slow down here for just a second, because the universe literally runs on these 4 primary laws, and they dictate absolutely everything around us. The 0th law states that if system A equals system B in temperature and B equals C, then A equals C. It sounds incredibly obvious, I know, but it's the entire mathematical foundation of how thermometers work. Because of this law, the mercury inside a little glass tube can accurately tell us the temperature of the entire room outside of it. Then we have the 1st law, energy conservation. You can never create energy from nothing, and you can never destroy it. Energy just kind of puts on a new mask. It merely transforms, like the chemical energy in a log of wood, transforming into the thermal energy of a blazing fire. Next up is the 2nd law, which tells us that entropy, or disorder, always increases over time. And finally, the 3rd law dictates that as temperature drops down toward absolute 0, the entropy of a system approaches a constant minimum. It's basically the point where atomic structures freeze into complete and utter stillness. I want to pause on that 2nd law for a moment because it is deeply profound. Things naturally move toward disorder. Without actively adding energy to a system, it inherently decays into chaos. Imagine dropping a single bead of red food coloring into a clear glass of water. At first, it's a perfect, organized little sphere, but seconds later, it inevitably explodes into chaotic swirls, mixing until the water is a completely disordered pink. The irreversible nature of this is key. It will never naturally unmix itself back into a perfect red bead. It's a critical cosmic rule dictating the forward flow of time and energy itself. Section 4. Water and state changes. Earth's giant heat battery. Okay, here's something wild about our planet. Water has the highest specific heat capacity of almost any common substance. It takes an enormous 4.186 joules of energy just to heat 1 single gram of water by 1 degree Celsius. To understand why that's enormous, think about a metal playground slide on a sunny summer day. Metal has a very low specific heat capacity, so the sun's energy heats it up instantly to a painful degree. But water takes a massive amount of energy to heat up. However, the flip side is that once water is hot, it holds on to that thermal energy for an incredibly long time. Because of water's wildly high specific heat capacity, our oceans basically act as giant thermal batteries. They absorb the sun's harsh heat during the day and slowly, steadily release it at night. This is exactly why coastal climates like San Diego or Vancouver stay so famously mild and stable year-round. Conversely, if you look at inland environments like the deep Nevada desert, which completely lacks that massive ocean heat battery nearby, you see blazing hot days followed by rapid freezing temperature shifts the exact moment the sun goes down. But what happens when we just keep pushing that energy? As you probably know, matter exists in 3 primary states: solid, liquid, and gas. As we continuously add heat to water, it crosses distinct physical boundaries. The solid ice melts into liquid water, and then that liquid vaporizes into a gas, or steam. Sometimes, under the right conditions, matter even skips the liquid phase entirely in a process called sublimation. If you've ever seen dry ice at a Halloween party turning instantly from a solid block directly into a thick, creeping fog, you've witnessed sublimation in action. Now there is a fascinating, kind of hidden twist in the physics right here. When a block of ice begins to melt, or a pot of water reaches a rolling boil, the temperature actually flatlines. It stays completely constant at its boiling or melting point, even as you are actively blasting it with more heat from the stove. Why? Because all that incoming thermal energy goes entirely into breaking the stubborn molecular bonds apart to force the state change, rather than raising the overall temperature. Scientists actually call this hidden, bond-breaking energy latent heat. Section 5. Newton's Law of Cooling, the real-world physics of cooling down. So Sir Isaac Newton didn't just discover gravity, right? He actually gave us the exact math for how things cool down. Imagine a hot espresso sitting on a table in a freezing cold room. Newton discovered that the rate a hot object loses heat is perfectly proportional to the difference between its temperature and the temperature of its surroundings. So at minute 2, when that freshly brewed espresso is vastly hotter than the room, it sheds its heat incredibly fast. But by minute 15, as the coffee's temperature creeps closer and closer to the room's temperature, that cooling exponentially slows down. And what makes this equation so incredible is how wonderfully universal it is. Newton's law of cooling isn't just about preserving your morning beverage. It mathematically explains how electronic capacitors discharge inside your computer, and it dictates the exact rate of radioactivity decay in nuclear control rooms. It is even actively used in true crime forensic science, because a human body cools down following this exact same exponential curve. Crime scene investigators can use the ambient room temperature and the victim's body temperature to mathematically rewind the clock and accurately estimate the time of death. It's literally all the exact same thermal math. Which brings us to Section 6, the universal heat engine. Heat powers everything. I mean it. Heat powers absolutely everything. This singular, invisible force drives the massive industrial turbines in our power plants and the combustion engines roaring inside our cars. It meticulously regulates your internal human biology, warming your blood so you can survive the winter. It acts as the grand atmospheric engine powering our global weather patterns, whipping up hurricanes and gentle breezes alike. And at the macro scale, under the strict, uncompromising laws of thermodynamics we just explored, it quite literally holds the fabric of the universe together. It all really comes down to this single, profound truth. The next time you feel warmth, you're experiencing the most fundamental energy transaction in the cosmos. Whether it's the bright sunlight hitting your face on a July afternoon, a warm meal settling in your stomach, or even just a tight hug from a friend on a bad day, that is thermal energy flowing from hot to cold, perfectly obeying the ancient, unbreakable laws of the universe. Which leaves me with a question for you. Knowing the strict laws of thermodynamics, the secrets of latent heat, and Newton's mathematical curve of cooling, what invisible energy transactions will you notice around you today? If you found this explainer fascinating, keep exploring, because as we've seen today, the universe has a whole lot more secrets to share. Thanks so much for learning with me.